Okay, there's one more lesson in this topic, and it's infinite geometric series. We've already looked at geometric series, but we'd like to study what happens if the series doesn't have an ending. Well, there's two different things that can happen. First of all, some geometric series grow without a limit because each term gets bigger than the previous one. Here's an example. 2 and 6, 18, 54, and so on. Each term is progressively bigger than what came before. If we don't have a limit on this, this won't have a sum. It will head to infinity, in fact. It's called divergent. Now, other series, they behave differently, and that's because each term gets smaller than what was there before. Here's an example. 4, 2, 1, half, and so on. Each of these terms is fairly small. So even though this series is infinite, the sum will converge, or head to, a finite specific number. Now, we can model that a bit on a calculator. What I've done is I've taken that series, starting with 4, common ratio of 1/2, and the exponent x minus 1 representing the terms. Now, we'll go to second function window, and we set independent to ask so that we can control the input variables. Now let's go second function table, and let's just check. If I enter 1, I get term 1. If I enter 2, I get term 2. So this is giving us the pattern that we're looking for. What happens as we add more and more terms? Well, what about the 10th term? You can see the 10th term is quite small, decimal 007. What about the 15th term? Oops, I put in 5. Let's go back and fix that. 15. Try again. 15. Oh, that's 515. I'm having trouble here. Enter 15. There we go. Now, this is a scientific notation. It actually means decimal 0002. If I enter 20, I get an even smaller number. So we are getting numerical results, we are getting terms, but the terms themselves are so small that they don't have much impact on the sum anymore. And that's only at x equals 20. So you imagine if I head out to 100 or 1,000 or beyond, that the size of the terms that I'm adding on are inconsequential. Okay, so what are the conditions for convergence? Well, if you look at those two series, we can see it was about the r value, and I need a small r value, specifically less than 1, so that I get the terms shrinking. Now, it could be negative, so we'll take care of that by saying absolute value of r less than 1, meaning the common ratio could be a negative small number or a positive small number. How do we go about summing? Well, we know that for a geometric series that we have this formula, a bracket 1 minus r to the n over 1 minus r. Well, if r is less than 1, what happens is r repeatedly multiplied by itself, that's what r to the n is, it heads to 0. It becomes inconsequential. Think about half multiplied by itself many, many times. It's very, very small. If that's the case, then 1 minus r to the n essentially becomes the number 1. Now, if I substitute 1 here, you'll see that I get the sum for an infinite series is a times 1 over 1 minus r. This is the formula for an infinite geometric series, when r is less than 1. That's the condition we need. So it's actually a simpler formula than we used before. Let's do a few examples. First of all, here's a geometric series. This has an a of 48, first term. It has an r value of 16 over 48, or 1/3. Notice that it says plus dot dot dot, meaning infinite. Because this r value is less than 1, there will be an infinite series. So I can say s equals a over 1 minus r. Let's substitute in my values. 48 for term 1. 1/3 for r. 1 minus 1/3 is 2/3. Division by a number can be thought of as multiplication by reciprocal. Let's divide out the 2, and I get 24 times 3, or 72. So even though term 1 was at 48, and I add 16, these terms shrink so quickly that even if I add them forever, the sum is only 72. Here's another example. Here's sigma notation again. Now, sometimes with sigma notation for an infinite series, you'll see the infinity sign, meaning k takes on the value 1 and keeps on going forever. Other times, there'll be nothing there at all, meaning k starts at 1, but it has no end. They mean the same thing. It's a good idea to expand this just to see what's happening. Exponent 1/2, I substitute 1, that's a 0. Next I substitute 2, leaving exponent 1. Next I substitute 3, leaving the exponent 2, and so on. So this is 4, and 2, and 1, and so on. This is the infinite geometric series I started the lesson with. Alright, well, we can see that we have an a value of 4, and we have an r value of 1/2. You might want to look at the sigma notation to see where the 4 and the 1/2 can be found. Because this is infinite, the r is less than 1, then I have an infinite sum. So a over 1 minus r is going to become 4 over 1 minus half, which is 4 divided by half, or 4 times 2, which is 8. So this sum added forever is 8. Kind of a surprising value, considering that the first 3 terms themselves are 7, and yet if I add forever afterwards, I will only arrive at 8. You may want to play with that on your calculator a little bit and see why that is. I've got one more example for you. A word problem, application. It says a ball is dropped from 10 meters off of a roof and it rebounds 70% of its height after each bounce. We may want to draw a little picture of that just to get a visual of what's going on. There's my fall of 10, my recovery, fall, recovery, fall, recovery, etc. Going on and on. This is 10. Okay, well, I want all the distance traveled. That's all the downs and the ups and the downs and the ups, isn't it? Well, I've got 10 down. That's my A. My R is 0.7. And after this, you can see that I go both up and down. So this is actually 10 times 0.7, and so is this. This term over here is 10 times 0.7 times 0.7, and so is this, and so on. So I actually have to modify this 10 a little bit. I actually need to use 10 times 0.7. I'm going to use this as my A. And I'm going to make a little adjustment to that. So I'm going to call it 7. 0.7 of 10 is 7. Now it does that upward and downward, so it does 2 of those. So A is 14. So what I'm doing is I'm leaving this initial part because it doesn't match the pattern of anything else. Everything else is doubled sets. I'm going to add 10 on the end. So I want the sum of an infinite number of terms based on A over 1 minus R. Alright, that's how to get the infinite sum. The only thing I have to do is I have to add 10 on for that first part that didn't fit the pattern. So that's 14 over decimal 3 plus 10. Now, decimal 3 is 3/10, so I can write this as 10 over 3 and 10. Or I could turn on a calculator and get a decimal value, since that's what I'm going to end up with anyway. And so when I do the sum of this, I get 56.6 repeating, and I guess the units are meters. There you go. Those are several example questions to show you how infinite series for geometric work.